Welcome everybody to Algebra 2, Section 6.1, nth roots and simplifying radicals. So to start off here, we're going to do a little bit of a warm-up, and that's just listing our perfect squares, perfect cubes, and perfect fourths. That's new to us. And perfect fourths is just powers of 4 is all. Once again, these aren't things I'm asking you to memorize, but it is helpful to know how to generate a list and to recognize them. Remember, we can always generate lists by utilizing our calculator of doing 1 squared, 2 squared, 3 squared, or 1 cubed, 2 cubed, 3 cubed, or 1 to the 4th, 2 to the 4th, 3 to the 4th. So, perfect squares, we're going to do the first 10 of each of these. 1 squared is 1. We get 4, 9, 16, 25, 36, 49, 64, 81, 100, ... Perfect cubes. 1, 8, 1 cubed, 2 cubed, 27, 64, 125, 216, 343, 512, 729, 1000, ... Now, I don't have any of these perfect fourths memorized except for 1 to the 4th and 10 to the 4th because, well, I should say in 2 and 3 to the 4th and 4 to the 4th. But past that, I don't have these memorized, but I might just know how to find some of them. Quickly maybe in my head, but otherwise, once again, I don't really bother working with these much. So 1 to the 4th is 1, then 2 to the 4th is 16. Then we get really big really fast, going up to 81, 256, excuse me. You'll recognize some of these appear on other lists, perfect squares from before. 625, 1,296, 2,401, 4,096, 6,561, 10,000, and ... Now, nth roots, let's talk about that. So, x is the nth root of a real number a if x to the power of n equals a. So we're just saying x is being raised to some power n, thus there can be an nth root. You can do a root of that. Similar to how if we had like x squared equals something, you could have a square root, or x cubed equals something, you could have a cube root. Very similarly, it's just an nth root here, because nth just is in the place of any number, any exponent. So examples here. So, for example, 9 and negative 9 are both square roots of 81, because not only is 9 squared 81, but negative 9 squared is also 81. The parentheses there are important because that tells you to do negative 9 times negative 9. Negative 2 is the singular cube root of negative 8 because negative 2 to the third power is negative 8. Now, there were 2 square roots for 81, but only 1 cube root for negative 8. And that'd be the same thing if it was a positive 8, it'd just be a positive 2, it'd still be 1. And that's because when you do an odd number of multiplication, so when you're multiplying an odd number of things together, in this case 3 things together, there's all negative 2, you're going to end up with either a negative or a positive depending on whatever you started with. Whereas whenever you do an even number of things multiplied together, such as square roots or even fourth roots, you're always going to end up with a positive. So fourth roots of 256 are both 4 and negative 4. Because once again, an even number of positives is a positive, and an even number of negatives is also a positive. So 4 to the 4th is 256, and negative 4 to the 4th is the same, 256. So in general, even roots will have 2 answers, and odd roots will have 1 answer once we're finding nth roots. But what we're going to be doing today is actually just simplifying radicals, and so we won't be necessarily doing that. But let's talk about a little bit further about nth roots before that. So the nth root of real number a can be written as the radical expression nth root of a. So instead of saying it's like the square root of, whatever, 81 perhaps, we're saying that we're going to have a little number here. And that number is what we call our index. And that index tells us what root it is. So for example, if this was originally x squared equals 81, and then we went and we did the square root on each side, then we would end up putting a 2 here as the index. Now, when we've never written that 2 there before, so why are we writing it now? Well, that's because if you don't write a number there, it's technically just implied that it's a 2. Very similarly to how if we just write an x, it's assumed it's an x to the first, or it's assumed it's a 1 times x. And so in the same way, when we write a radical or a root, and we don't put a number here for the index, we assume that it's 2. But what would happen here is because we do the square root, this is technically a 2 there, which once again, we don't need to write because we assume that the 2 is there. Now this itself is our radical, or the radical sign. And what is inside or underneath the radical sign, or the radical, is what we call the radicand. These vocab words are going to be important here. I'm going to be utilizing them throughout this section and a lot of this unit. They're also going to be important here in this table. As you notice, it uses index radicand in the table. Now, if there's no index, that's what I was talking about a moment ago, it's assumed that the index is 2, or n equals 2. Now, I do want to clarify that when we write that index, we do want to write it just small and up there. We don't want to write it super massive. That way it's not confused as a number multiplying with the radical. So now, if our index is even, whether it's positive or negative for the radicand, so what's inside is positive or negative, we're going to get 2 answers. So if our index is even, aka a square root, a 4th root, and a 6th root, as we talked about up here, we're going to get 2 answers whenever that happens. So number of roots is going to be 2 for those. Now, when we square root a positive number in the past, such as 81, we know we've gotten real roots, such as 9. When we square root a negative number, such as negative 81, we know that we get imaginary roots, or as I like to call them, the lateral or complex roots. Now I should note that the number of roots here, you get 2, and it's both the positive and the negative. That's important to clarify, the positive and the negative for the signs. We often write it with like the plus minus, so here we'd write like plus or minus 9, for example, positive, negative, square root of 81. Now, if your index is odd, so such as a cube root or a 5th root, which we'll only really be dealing with the cube root for odd roots, and the radicand is positive, you're going to end up with the real roots. You'll just get one of them and it'll be positive. And if it's an odd index again, so once again that cube root, for example, and the radicand's negative, so such as cube root of negative 8, which could be written as cube root of negative 8, would get you negative 2. And so you'd get a real number again, and you get one number, and it's negative. So even indexes, or even roots, will always result in 2 answers. Whereas odd indexes, or odd roots, I don't really like that this says roots there. I'd like it more to say answers. But because really I'm going to call this this whole thing a root. But anyway, an even index or even root, so like a square root or a square index or index of 2, would lead to 2 answers all the time, both positive and negative. Whereas an odd index or an odd root, such as a cube root or an index of 3, will always lead you to one answer that is the same sign as what you started with. So the cube root of a positive is a positive. The cube root of a negative is a negative. Because once again, as you cube a positive, you get a positive. As you cube a negative, you get a negative. Now, if a radicand has more than one nth root, the radical sign indicates only the principal or positive root, aka what this is trying to say is on a problem like this, actually, if you're just given the square root of 16, that's just saying 4. It's not saying positive or negative 4. It's just saying 4. Now, the reason why it's just saying 4 here, but up here, I said it's saying positive and negative 81, positive and negative 9, excuse me, is because here we're undoing a square by square rooting. And whenever we undo the square, whenever we undo an exponent and we actually apply the radical ourselves, then we have to indicate, put that plus minus there. Whenever the radical's already there and we're not undoing an exponent by putting it there, or in order, to put it there, then it's just going to be the one answer. So for example, another example here, negative square root of 121 is, well, square root of 121 is 11, but then make it negative 11 is what that's saying. And so we assume that this is a positive there, we just don't write the plus sign, is what that's getting at. So up here, this is getting at, once again, sorry I didn't make click out of that. This is getting at right here that we just don't write the plus sign here. We just assume that's positive. Whereas here, we write the negative sign. So now the square root of 289, well, that would be 17. The negative square root of 4 over 25, remember you can split that up into two smaller square roots. I recommend that. Would be 2 over 5, but it is a negative somewhere on there, whether the negative's on the top or the bottom or the out in front of the fraction, it doesn't even matter a little bit. Next, cube root of 8 is 2. Cube root of 343 is 7. You may be wondering, Mr. Kossel, how are you finding these? Well, we can go back to our list and count. Or if you are struggling with that, we can also utilize our calculator. How, you may ask, since there's no square root button we can see. Well, fine math students, let me show you by going to my camera on here and showing you a calculator. Don't mind the shaky cam here as I'm having to hold it. And so we go to this math button right here, right below the green alpha button on these handy dandy TI-84s. And as you're in this math button, in this first menu that just says math here, you don't have to go to any of the other menus here. Sorry for citing the calculator. The fourth option here is the cube root. The third option is cube, but the fourth option is the cube root. And so then we hit enter there, and then it says cube root of what? What it says on the screen. And so we can type in the cube root of 343, for example. And it says it's 7, just like we said a moment ago it was. Now, in a moment, we're going to have to be doing higher roots than 3. So what do we do for that? Well, once again, you can go to the math button. And this time we just hit option 5, where it says X root. And it now allows you to type in a number for the root 2, or the index. And so I would type in the fourth root of whatever number I want. So let's say I want the fourth root of 256. And then I can arrow out of there if I have more to write. And it tells me it's 4. How neat is that? So back to, it wanted to load. And now it's wanting to say I didn't have all of the writing on there, but give it a second, it'll pop back up. It always does. There we have it. So the cube root of negative 125 is negative 5. Just type in the negative of your calculator to help you. Cube root of negative 1 over 27, once again, you can split that up into 2 different cube roots. Otherwise, your calculator could help you as well if you just type in cube root of negative 1 over 27. However, your calculator might just give you a decimal as your answer, which is not necessarily what we're looking for. We want fractions as our answer, which is what I'm going to ask you to do. So you'll probably have to type it in as 2 separate problems if you need to type this stuff in. So cube root of 1, cube root of 27, and then make the fraction on your own. This would be 1 over 3, or negative 1 over 3. The negative fourth root of 1 is negative 1. The fourth root of 2,401 is 7. The negative fourth root of 4,096 is negative 8. And the fourth root of 81 over 16, once again, we could do the fourth root of the top number, the fourth root of the bottom number, and we end up getting 3 over 2. On to the next page. We're going to work on simplifying radicals. How exciting. We have 2 to start off that are just simplifying square roots, which is what we've been doing before. So this is not new to us. We like to find the biggest perfect square that goes into or is a factor of 117, or the radicand, what's underneath the radical. So to do this, it can be helpful to have that list of perfect squares available. So that 1 squared, 2 squared, 3 squared, so on and so forth. This ends up being square root of 9 and square root of 13. And that is 3 square root of 13. Well, for some reason it decided to say that was 13 square root of 13, but it is 3 square root of 13. And remember, we don't have the positive, negative, plus or minus, because we did not actually go to the work of undoing a square. It wasn't x squared equals 117 in a previous step. And we didn't actually write square root to undo that. Otherwise, in that scenario, we would have a plus or minus here. On to number 2, 4 times the square root of 320. Well, that's 4 times the square root of 64 times the square root of 5, which is 4 times 8 times the square root of 5. 32 times square root of 5 is our result. Now let's move on to cube roots. Oh, the moment I'm sure many of us have been waiting for. So, just like I said a moment ago, it'd be helpful to have our list of perfect squares handy. It's helpful to have our list of perfect cubes handy for this. So in the same exact manner that we would look for biggest perfect square that was a factor, we want to look for the biggest perfect cube that's a factor. And instead of writing multiple square roots, we're going to write multiple cube roots. So the biggest perfect cube that is a factor of 48 is 8. And so that'll be 2 times the cube root of 8 times the cube root of 6. It still works the same way to where 8 times 6 is 48. So the cube root of those numbers is the cube root of 48. Now the cube root of 8 is 2, just like the square root of 9 was 3. And the cube root of 6 is the cube root of 6. That can't simplify any further. There's no smaller cube roots than 2 other than 1, and that doesn't make our numbers any smaller. So then we multiply the 2 and the 2, the regular numbers together, the non-radicals, and we get 4 times the cube root of 6, and we call it good. Then on number 4 now we have 3 times the cube root of 108, and so we need to find the biggest perfect cube that is a factor of 108. Once again, it's helpful to consult our list and then start dividing by different numbers in that list. So 108 divided by this and that and the other, and start with any number smaller than 108. But we want to find the biggest perfect cube, start with the first number smaller, aka the biggest number that is still smaller than 108. So in this case, like 64, then 27, then 8. So here it would be 3 times the cube root of 27 times the cube root of 4, which would be 3 times 3 times the cube root of 4, which is 9 times the cube root of 4. Now, a lot of us might think naturally, like, what, cube root of 4? We could do more there, but we can't. We could do it more if it was the square root of 4, but not now because it's not the square root of 4, it's the cube root of 4. All right, same thing here on number 5, except for now it's negative, so it's not going to lead to an imaginary number, though, because we can have cube roots that are negative. It's just going to result in a negative number. So biggest perfect cube, that's a factor of 250, is negative 125. And the cube root of 2. Now, when the cube root is negative, we do want to have still want to simplify the negative out by doing the perfect cube and making the perfect cube the negative one. Because technically 125 times negative 2 would still be negative 250, but we want to make sure our perfect cube is the one that is negative, so that way we are simplifying the negative out of the radical. We want our inside of a radical, the radicand, to end positive. So the cube root of negative 125 is just negative 5, and so we get negative 5 times the cube root of 2. On number 6, 6 times the cube root of negative 2. Negative 2, I can't simplify any further, but I mentioned that we don't want the negative inside the radical. So what we're going to do is say that the cube root of 2 is the cube root of negative 1 times the cube root of 2. Because now we can say the cube root of negative 1 is just simply negative 1, which is true. And that makes it so that our radicand, or the inside of the radical, is positive. And so we get negative 6 times the cube root of 2 as our answer. On the number 7 here, fourth roots. So same idea. We're looking for factors that are perfect fourths of the number of the radicand, in this case 162. So here the list is really helpful. So remember the first few, and since the numbers get so big, we're only looking for the same few every time, which is the nice part. So 1 to the 4th, which we won't really be looking for. 16, which is 2 to the 4th. 81, 3 to the 4th, 256, and 625. And I'm not even going to go beyond that because more than likely we're not really going to be using many numbers bigger than that. Ooh, I say that and then I actually looked at another one and realized we're going to be using that, so I spoke too soon. The next one would be 1,296. And now I'll do the dot, dot, dot. So 3 times the fourth root of 162. So the perfect fourth, that is a factor of 162, would be 81. And so it's 3 times the fourth root of 81 times the fourth root of 2. And so it's the same process for all of these, whether it's square root or third root or fourth root. All that changes is the list of numbers you're using. So they're using this list or the perfect cubes, the perfect squares, and what numbers you're writing here. So that'd be 3 times 3 times 2, or sorry, the fourth root of 2, because the fourth root of 81 is 3. And so that results in 9 times the fourth root of 2. On number 8, big number. We want to check the first one that's smaller than it. First one that's smaller than it is 2,401, not a factor. The next one, 1,296, is a factor, thankfully. So 5 times the fourth root of 1,296 times the fourth root of 2 gives you 5 times the fourth root of 1,296 is 6 times the fourth root of 2. And so that results in 30 times the fourth root of 2. Now let's do some simplifying radicals that have variables in them. This is new to us. Well, essentially, it goes back to remembering that when, we multiply and do x squared times x squared, we get x to the fourth. So squared is a bad example there. Let me go x to the third and x to the third. That'd be a better example. We get x to the sixth by adding them. But when we do x to the third to the second, we multiply them. Now, the reason that's going to be helpful here is because it's going to work in reverse. It's going to work in reverse of this one or this one, depending on how we think of it. So either way, 6 is a multiple of 3, 6 is a multiple of 2, so depending on our problem. Now, I say multiples because you notice the word multiple is going to appear here, here, and here. So for square roots, when the index is 2, exponents must be multiples of 2. For cube roots, when the index is 3, exponents must be multiples of 3. And for fourth roots, when index is 4, exponents must be multiples of 4. And by that, we'll see what we mean in just a moment. So the square root of 32, x to the fourth, y to the ninth. So the perfect square portion is the square root of 16, and I'm going to leave a space on purpose. Then imperfect square is the square root of 2, because 16 times 2 is 32. Now, we said x, they must be multiples of 2, so we want to take as many, we want to think essentially, what's a good way for me to phrase this here? We want to say, okay, is 4, scratch that. I'm going to change up what I'm saying here. I'm going to go ahead and do the numbers how I've been doing it, square root of 16, square root of 2, and call this 4 times square root of 2. For the exponents and the variables, I'm going to say we do this number divided by this number. We do 4 divided by 2. And we get 2. And so this ends up being 4x squared. The 2 is what happens there, because 2 goes into 4 2 times. Multiple of 2. What about 9? 9 is not a multiple of 2. Well, 9 divided by 2 again, this number divided by the index, is 4 with a remainder. So y to the fourth with a remainder of the y. So that remainder of y, the 1, is a y to the first inside the radical. I'll explain that again. So how we simplify those exponents is we say, how many times does this index go into the exponent? The answer for x was 2. The answer for y was 4. If there's any left over, so for the x there were no leftovers, it went in 2, and after it went in twice there were no leftovers when you divided. For the y's there was a leftover of 1 y left. Because if you go in 4 times, that gives you 8 y's, y to the 8th. If there's any left over, it goes on the inside there of the radical. And so that ends up being our answer. Let's work on number 10 here. The square root of 324 a cubed b to the 7th. So the square root of 324 is the square root of, it's actually just perfect squares, it's just 18. Now we do 3 divided by 2 for a, and that gives us 1. So we have a to the first and 1/2. So inside the radical, we'll have a to the first. Now I'm leaving a space here because I know I'll have b. For b, we do 7 divided by 2, exponent divided by index, and 2 goes into 7 3 times. So we have b to the third outside the radical. And there's a remainder of 1, and so this 1 goes back in the radical. And so we have 18ab cubed times the square root of ab. Cube roots and fourth roots work very similarly to that, except for instead of dividing by 2, you're dividing by 3, because that would be your index. So on number 11, cube root of 216, m to the third, n to the 6th. Well, cube root of 216, that's actually a perfect square. It's just 6. For m, you do exponent divided by root, our index. So 3 divided by 3 is just 1. So m to the first, with no remaining. So there's nothing inside the radical for m. For n, it's 6, the exponent, divided by 3, the index. That gives you 2 with none remaining. So it's n squared with nothing inside the radical. So this just results in 6mn squared. On number 12 here, we actually do have to simplify the cube root of 56, not just a perfect square. So I will say the cube root of 56 simplifies to the cube root of 8 times the cube root of 7. The cube root of 8 is 2. So we get 2 times the cube root 7. I will also do my variables. So I do my numbers in one section, I do my variables in another. R to the 8th is really 8 divided by 3, exponent divided by index. 3 goes in 8 twice, with 2 remaining. And so we end up getting 2r squared on the outside so far. Then s to the 4th will be 4 divided by 3, exponent divided by index, which 3 goes into 4 once, with 1 remaining. And so it'll be s to the 1st outside the radical. Inside the radical will be the cube, inside the cube root or the radical will be the 7 from earlier, the r squared, and the s to the 1st. And that would be our answer. So I just take these as 3 different parts. Number, first variable, second variable. And if there's 5 variables, for example, then I take them as 6 parts. Number, and then each of the 5 variables. And then at the end of the problem, sorry, I realized I was going to say something after I started zooming out. At the end of the problem, I say, okay, everything outside the radical, so this regular 2, the r squared, and the r to the 1st, or the s to the 1st, are all outside the radical. Now, it is important for us to be careful here that we don't think this 3 is on the s. And so we need to make sure that we're very careful with our handwriting here as we're interpreting these. And if you ever have a clarification or something you want to clarify, like on a homework assignment or a test, as you see something printed of whether the number you see is an index, aka on the radical, versus an exponent on a base, then I just ask. Number 13, cube root of negative 64 x to the 10th, y to the 21st. So the cube root of negative 64 is negative 4. The cube root of x to the 10th, that's going to be ten over 3, which is 3 and 1/3. And the cube root of y to the 21st is 21 divided by 3, which is 7. So negative 4 is outside the radical. X to the power of 3 is outside the radical. And y to the power of 7 is outside the radical. Nothing from the numbers is inside the radical. X to the 1st is inside the radical. And nothing from the y's is inside the radical. So this is our answer. Once again, just doing a step-by-step approach. On to number 14. Once again, I'll do a step-by-step approach here. So the cube root of negative 81 is the cube root of negative 27 times the cube root of 3, which is negative 3 times the cube root of 3. The cube root of p squared, we divide 2 by 3, which 3 never goes into 2, so it just stays as 2 over 3. The cube root of q to the 12th, we divide 12 by 3, and we get 4 with none remaining. So now we say, okay, negative 3 is outside the radical. No p's are outside the radical because there's 3 nodes doesn't go into 2. But 4, q to the 4th, is outside the radical. And we have our cube root. We have a 3 inside the radical. We have p squared inside the radical. And no q's, because there were none remaining. And that is our answer. On 15 and 16, we get the pleasure of doing this with fourth roots. So I'm still just going to split this up, part by part. Fourth root of w to the fourth. So, just like before, exponent divided by index. So 4 divided by 4. So 4 divided by 4 is the whole number 1. Then the fourth root of v to the 17th. 17 divided by 4. 4 goes into 17 4 times with 1/4 left over. So then, for our answer, we have w to the first outside the radical and v to the fourth outside the radical. Again, inside the radical, we don't have any more w's, but we do have v to the first. On to our last problem for the day, number 16. We'll have 3 different parts, one for the 48, the m to the 8th, and the last one for the n to the 3rd. So the fourth root of 48 to start. 48 is not a perfect fourth, so we split that into the fourth root of 16 and the fourth root of 3, which is 2 times the fourth root of 3. The fourth root of m to the 8th, we do 8 divided by 2, exponent divided by index, which results in 4, with none remaining. Then, for n, the fourth root of n cubed, we do 3 divided by 4, once again, exponent divided by index, which results in, it doesn't. 4 never goes into 3. So as we write our final answer, 2 is outside the radical, m to the fourth is outside the radical, and there are no n's outside the radical because 4 never went into 3. Inside the radical, we have 3, no m's, and n to the 3rd. And that wraps up section 6.1.